Hello, this is Kamyab Cornett, and this is Lab 4 for Physics 2211. The goal for this lab was to generate a model to predict motion and compare it to the motion we tracked in the video. To compare this motion, we used Tracker, and we also wanted to record energy changes in the system. After conducting and making the code, we found that the model is a good predictor for string motion in some ways, and the total energy change is 0. A key concept in this lab is Newton's second law. In using Newton's second law, we can find the velocity and position update formula, which we used in the code to track the spring's motion. Another important concept is the energy principle, which is used and modeled in the code as well. Kinetic energy was used in the code to model the spring's motion, as was spring potential energy and gravitational potential energy. In this instance, the system is the mass hanging from the spring, and the surroundings are gravity, the spring, and the general atmosphere around it. Our initial conditions are that per the lab instructions, our string starts at 0.7 meters. The coordinate plane starts at the top of the spring stiffness is 6.83 newtons per meter. The starting position is negative 0.110. In the x position, negative 0.636. In the y position, 0 for the z position. And the initial not stretched length of our spring was 0.123 meters. For this procedure, we used the video that was provided for us in Canvas. I used Tracker to collect the data points. Some of the data points, not all, are displayed on the right side as an example. These data points were then transferred to Excel sheets and converted to .csv to be used into the code later. Through Canvas, we found that the ball was 0.402 as mass. The position vector from Tracker was negative 0.110 in the x direction, negative 0.636 in the y, and 0 in the z. The delta t was 0.095. The spring stiffness was also taken from Canvas, and so was the relaxed length of the spring. The L, L hat, and S vectors are updated accordingly as shown, and the kinetic energy, gravitational potential energy, spring potential energy, and total energy are also modeled in the code in this graph. Following up with the code, at the top we have the gravitational vector, gravitational force vector, the force of the spring, and the total force, which is a combination of the force of the spring and the force of gravity. The rightmost code is used to track the difference from what was tracked in Tracker and the difference from the model. This part of the code is essential because it helps model the effectiveness of the code. Each one of these graphs is important for the code and tells us a different thing about our model. In the bottom, we have the change in energy versus time, and we can see that the change in gravity and the change of the spring are inverse, and the kinetic energy helps balance it out and make the total energy delta E 0. As we can see, the x position was better modeled by the code than it was the y position, but both are fairly accurate. As previously mentioned, the energy from gravity and from the spring were inversely proportional, and for the position versus time graph, it was fairly accurate. However, the x graph was a little bit more accurate. Some potential errors include not accounting for some other forces, like friction from the air, the loss or gain of thermal energy, or even rotational energy. Well, what does it mean? After conducting the experiment, we can find that the energy principle is satisfied. The energy of the system is 0, and that's because using this formula we find that delta E, the change in energy, is equal to the change in kinetic energy, the change in gravitational energy, and the change in energy from the spring, which from the graph we can find all add up to give us a total change in energy of 0. In the graph we see that the change in gravity and the change in the spring are inverse, and K works to balance out delta E. For the second what does it mean question, we find that the average oscillation period of the x coordinate is 1.614 seconds, and for the y period it's 1.519 seconds. That gives us a difference of 0.095. The differences could cause a different value for K, which is the stiffness, and a different value for the spring force or potential energy. This could could be the result of incorrect tracking in tracker or not accounting for other forces. Thank you.